Jonathan are going to be talking about distributed HPC applications with unprivileged containers.
Thank you, Stefan. So I'm Felix, this is Jonathan. We work at NVIDIA and in California, and we're going to talk about our infrastructure, how we use containers for multiple different applications. So let me get something out of the way. I know we just got Steam, and we are from NVIDIA, but we don't do video games. And so people, sometime when I go to a conference about Linux and containers, they say, why are you here? You're NVIDIA, you do Windows and games. But that's not only what we do, actually. So our latest GPUs do ray tracing with RTX, so that's useful for games, but also for visualization, professional visualization, for movies. And in the middle, we have a type of GPUs that's only used for crunching numbers. So like astrophysics, biology simulation, mathematics, machine learning. We have GPUs that don't have a display. They don't have a display. You put them in a data center and they just crunch numbers like deep learning or what we call HPC, high performance computing. And on the other end of the spectrum, we even have autonomous machines like robots, self-driving cars, so it's like more like smaller system, embedded systems that people can use for computer visions and kind of real-time tasks that are involved. So we call that GPU computing, and you might have heard of CUDA. That's our platform for doing that beyond video games. Okay, so we at NVIDIA, we have an infrastructure we have multiple clusters, multiple data centers in Santa Clara. And we have one that's per some benchmark, the top 500, that's a measure of supercomputers. We are number 20 in the world. And those are very, very large machines right here. We have 16 GPU, each more than 400 watts. So with a total of 12 kilowatts per machine, and we have 96 of those, 1.5 terabyte of RAM. So those are machines that are gigantic. InfiniBand for the networking, because we need very fast networking. And pretty uncommon, we run Ubuntu, a little bit uncommon in HPC, but that happens. So the next talk is about, I know the next talk is about Raspberry Pi, and that will be a lot of Raspberry Pis to reach one node here, 12 kilowatt. 4 years ago, Jonathan and myself, we started a project called NVIDIA Docker, and then evolved into libNVIDIA Container. And the goal was to make it easy to deploy your CUDA applications in containers. And so it worked pretty well. And now it supports all runtime, so that's good because it doesn't force us to use a specific runtime. We can use LXC, we can use RunC, Docker, Containerd, Kubernetes. You can run your CUDA apps in there. And especially we use containers at NVIDIA for deep learning and HPC because we know some of these apps are difficult to package, to install, and they sometimes conflict between each other. So we put that in a container and we put that on Docker Hub or some of them in our own container registry. People can download those and have a stack already installed for TensorFlow, PyTorch, biology and stuff like that. And so we use containers for a lot of things, even benchmarking, and especially for machine learning, deep learning. So I've mentioned our hardware, but let's take a look at what a typical cloud deployment looks like. So you don't have nodes usually like we have, 12 kilowatts. You have maybe smaller nodes, instances on AWS, hundreds of thousands of them, and you containerize for security. Not for sometimes for packaging, but also for security. And you have microservices, so maybe 100 containers per node. You have traffic from the outside world. You have user uploads and stuff like that, internal traffic. And you don't use that. Users don't access the cluster directly. They basically ask someone if they can deploy a new app on the cluster. And you have advanced features that I've listed here, but so that was kind of the Kubernetes, what Kubernetes has to offer. So going to what we do at NVIDIA, as you've seen, very large nodes, and we kind of trust the users because our cluster are sometimes air-gapped or very little access to the outside. So if someone hacks the cluster, if someone uses 0 day on our cluster, I mean, we're just going to fire him, and that's pretty much it. We run trusted code on our clusters. So, and also not all applications are containerized. If an application is not containerized because it's packaged well, don't use a container. We don't want people to force users to use a container. because they did their job correctly. So this actual step is actually eliminate Kubernetes already, because Kubernetes is fully containerized everything. And we have few applications per node. We are not very dense. We have multi-node jobs also, which means that you need to start 30. You need to start the job on 30 nodes in parallel, so it takes a bit of time. And as I say, mostly little traffic to the outside world. So, we are not choosing Kubernetes, unlike maybe many people before us. We have chosen something that's pretty classic in HPC called Slurm. So it was way more adapted to our use case. So it has advanced scheduling algorithms, so for quotas, teams and stuff like that. And especially it supports gang scheduling, which means that if you need to run on 30 nodes, there is no need to start running unless everyone is ready. Because if you start running on 50 nodes, you're just going to spend CPU cycles waiting for the other 15 nodes to join. So you really have to make sure that they are all ready at the same time and start at pretty much the same time, otherwise it's just waste. Low runtime overhead, the control plane is pretty small. Topology aware, so that if you have NUMA machines, you optimize for performance in the allocation. And it's user-centric, is that you submit a bash script, it will run your bash script. You can SSH into a login node and then have an interactive session on a big machine like we showed. And it supports GPUs, and well, the only drawback was it did not support containers. And we use containers especially for deep learning, machine learning. So, but it does support plugins. So what we did is we looked at our requirements, and we need performance. We need no overhead in the container runtime. We need to support Docker images because our researchers still install Docker on their machines, because that's convenient. That's a nice UI, Docker build. Everything is nice. We need soft cluster multi-tenancy, so that means that you can have multiple users on the same machine, but you just want to make sure they don't steal resources from someone else. We are not trying to really strongly isolate between, so it's not a security boundary, just you have 2 CPUs, you have 4 CPUs, and you cannot take more. And we need GPU support, Mellanox for RDMA for networking, and multi-node jobs, so the runtime should not get in the way of all of that. And also interactive containers. You can install package, ptrace, strace, GDB, your process, everything like that. So there was no container runtime that really filled this need, so it was actually simpler. It was simpler still to use Slurm, but use their plugin system to create a new one and integrate it than modifying Kubernetes for our needs. So that's what we did. Before I hand over to Jonathan, just want to mention that, get something out of the way first, is that writing a secure privileged container runtime is very, very hard. So there's this presentation by Alexa from 1 month ago or so. So you really want to have something that, you really have to use what we call user namespaces. And that's basically the point of his talk. So you avoid a lot of issues. And so if you get that out of the way, writing a container runtime is not actually that difficult. We're not going to explain how to write a container runtime because there's a lot of talks about this already, but we're going to explain more the reasons why we did what we did. And the last point being here that even if you trust your users pretty much like you do, there's still a lot of accidental damage that can happen if you still give real root inside containers for users, like access to files, or breaking the system, or being able to debug from outside the container to debug the container, because if it's run as UID 0, you might not be able to debug it. So our runtime is called nroot, and I will hand off to Jonathan to explain each topic here on this list.
Right, so we're going to go through some of the design principles that are listed here. And to be fair, it's heavily influenced for LXC. So the first thing we did was we actually used user namespaces. The reason for that is we wanted a fully unprivileged container. The difference with other runtimes, though, is we only have one user namespace mapping, which basically maps the user that's outside of the container is the same user inside, so they have the same UID. And optionally, we let them also remap themselves as root inside the container. And why we have both choices is because some application refuse to run as root. and some need actually root access or fake root access. We also like keep the same username inside the container for just convenience, as not to confuse people, and we can automatically mount home and other things inside the container. Also, like note that like runc or like Docker-based containers, they always remap root inside the container, and we don't. So we talked about other runtimes, and like traditional runtimes, they usually use sub-UID and sub-GID maps for user namespaces. And they do that because they want to allocate a huge chunk of UIDs and GIDs. And we don't really do that because we run application containers. We don't need like this UID separation. But you kind of have to when you start installing packages, because you usually need to be root, and you need to have additional UIDs and GIDs because the packages will try to install new users and new groups. Plus, like there's also a problem with sub-UID and sub-GID maps is that you have it's difficult to maintain across a cluster. They have some efforts in shadow utils and stuff to solve this problem, but right now it's kind of difficult. And you can also run into permission issue once you like exit the container. Then you have to deal with like permissions that were inside the container are now different outside. So to solve that, we basically use a seccomp filter, and we trap all the set UID syscalls to make them succeed, even though they don't have a mapping inside the container. We also wanted like a standalone runtime with low overhead. So basically, there's no daemon involved. There's no persistent spawning daemon. And we inherit all the C groups from whatever was above us. So it could be systemd, it could be Docker if we're running en route inside Docker, or it could be Slurm itself in our case. For Dockers, people are really confused by that because you actually use the C groups from the Docker daemon and not from the Docker run command. And that's kind of the behavior we wanted. Also, like basically after the runtime has executed the application, it's out of the picture. So it executes the application and just disappear. So you don't have any other process hanging around like runc or Docker have like to handle PTY or exit or tracking containers. So we don't have that. We also wanted minimal isolation, so we don't need like this fancy network namespace with like overlays, or we don't need an IP for each container. We don't need to bind privilege port. We also don't want a PID namespace because it tends to confuse some programs, as we saw before. And also like handling PID1 is pretty tricky. And we've seen a lot of people like running sleep as PID1. As I said, like we just want to keep the C groups that were handled to us, and especially that like the scaler is like has better insights on like what needs to happen, like if you can overcommit resources or not. And obviously it simplifies the runtime and improves the performance. And speaking of performance, some of like the problems you can get with traditional runtimes is you have a network namespace which like usually involves a bridge or NAT or overlay networking. So you had overhead there. You have seccomp and LSM, which can have overhead for syscall heavy applications. We also rely on shared memory a lot, so we need shared IPC namespace. And Docker and other runtimes also try to tune your R limits, which sometimes are not really adapted. So for example, maplock is pretty low on Docker by default. And something that's less known is like when you actually turn on seccomp by default on a lot of distribution, you turn on also specter mitigation. So if you're concerned about performance, then like we actually don't want that. Little note about MPI, which is like a standard for framework for message passing that we use to communicate inside a node or even outside. So MPI doesn't really like also PID and IPC namespaces, as we discussed. And the cool thing of having like a fully unprivileged runtime is that we can use cross-memory attach. So it's like the syscall is process VM write V, which is extensively used by MPI. And that actually requires ptrace access. So with traditional privileged runtimes, it's kind of hard to have that working. As for coordination with PMI and PMX, I don't really dwell on that, but we just we actually need to pass file descriptor to the actual container, so we link file descriptor inside the containers by default. The most difficult part is actually the importing Docker images in the runtime, because you have to deal with a lot of the OCI stuff, AUFS formats and other things. And we really wanted to speed that up because we pull like really big images. So what we do is we actually rely on overlay.fs to basically do basically we just want the kernel to do all the squashing of layers rather than like a sequential extraction like Docker or Emoji do. Also, we found out that like just using plain bash, like the parallel curl pipeline, it tends to be much faster than the Golang because some of the packages are not really optimized. And we weren't really fond of the format, like the VFS format, for example, that Podman or Docker have because it's huge on disk space. And if you were to use the overlay driver in Docker or other things, what they do is they actually keep the layers uncompressed. But you can't share the layers between users because you would need something like shiftfs or something to convert the arrays. So what we do is we actually share layers across the same across users in the same group, and we compress them with Z standard. And we have helper binaries for overlay because unfortunately overlay is privileged. It's unprivileged on Ubuntu, but it's kind of broken right now. So we have that, which is not owned by default. So only the admin can import images by default with Android. For the image format, we chose SquashFS, and we wanted it to be super simple. So basically, when we convert the Docker image, all the entry point becomes just /etc/rc. All the environment goes to etc environment, and the volumes goes to etc FSTab. And basically, when you land in the container, you can edit these configuration files like you used to, and restart the container, and it will just be picked up. We like SquashFS images because you can store that as a single file on the parallel file system and use it, pull that really fast internally, and also avoid like all the thundering hertz problems that you have when you kick in multi-node jobs and it starts pulling the image like 100 times. Also useful for air gaps where the admin can control actually what you can run, so it imports the SquashFS and just stores it on the cluster. And you can also mount it as a block device and have it lazily fetch, for example, through NFS or something. Finally, we wanted it to be super simple. So the runtime is actually just a simple shell script that's like 500 lines of code, and it uses just basic Linux utilities to set up everything. So it's actually easy for users and admin to customize everything if they want to. If there's something that they don't like in the runtime, they can change something. And we have users and system-wide configuration that you can drop in if you want the mounts or environment in all your containers on the system or all the containers of specific users. You can just write these configuration files. So now for the basic usage, you can just so basically you can do init import. You will just give it the Docker URI, and you end up with like SquashFS representing the entire image. Then you can store that and share it with someone. You can create then a container from this SquashFS image, which just unpacks the SquashFS under your XDG data path. And then you can start, obviously, stuff in there. So you can run NVIDIA SMI in TensorFlow, or you can also remap yourself as root and have the read-write root file system, so you can install packages as an unprivileged user. Some of the advanced stuff you can do also is you can start the actual image directly. In this case, we actually rely on Fuse to mount SquashFS, and all your changes are in memory. And the really neat thing that people like is actually being able to create self-extracting bundles. So you can do nrun bundle, and then you will actually have a run file, that what we call a run file, that includes the image and the runtime. So you can send that to anyone running Linux, and they can just run your container without any dependency. So if you have an experience you want to share with a coworker, you can send it by email, send Ubuntu by email or something, which is really, really practical, especially when you do cloud deployments as well. You don't have to install anything on the instance. You just drop this file and run it. Now, when you look at how it's implemented inside, we have few utilities that replace basically the Linux ones. They're really simple. It's basically 3 of them: nroot, nshare, nrun mount, and nroot switch root. And we have 2 other ones which are mostly used for Docker imports. If we were to use the actual utilities directly, you could write your own custom runtimes really easily. So here you just download the Ubuntu official root file system, you create new namespaces, and then you mount a bunch of things, and at the end you just exec switch root and run bash inside your container, and now you have a really simple like container runtime. And now I'll give the talk to Felix, which will explain the Storm plugin that we did.
Right, so we saw nroot, the runtime. So we actually give access to this runtime for users so they can use nroot start, nroot create, but we didn't want to have users learn something new because they are used to Docker, but for reasons that we have explained, we didn't give them access to Docker on our cluster. So they are used to the syntax above. With Slurm, the command is called srun. You just specify a command and it will run that on one node or multiple nodes. And you say, I want to run Python on one node. And Slurm has a lot of plugins, and it was very nice because we added the container image, -- container image flag, and you say, I want to run TensorFlow, and that's the only change in blue and yellow here. That's the only change that our users had to learn. They can still use nroot if they want, but we wanted to make it easy. They don't know about the container runtime, they don't know it's nroot, they don't know. It actually started as a prototype with LXC too, and it was the same syntax, because here, we don't need to be very complicated because our runtime is very simple too. We just want to say, run this image with mounts, and that's pretty much it. That's the basic. So a little bit of the details how we do that in Slurm, that we start the container. So right now it's with nroot, and we basically get the handles on the namespaces. We get the environment variables about the process, and we get the directory where the container is. But we cannot hijack the exec. We cannot hijack the exec Python train.py. So it's more like a Docker exec. What we do here in Slurm is we Docker exec that just before we go to the Python train.py, we do a bunch of setns calls to join the namespaces of the container we have created. And then we hand it back to Slurm, and Slurm will execute python.py. It doesn't know it has been containerized in between, but it actually just works. That works just fine with just those few steps. So quickly, as I said, we have just a few new flags. So you can name a container. If you do container image PyTorch, it pulls that from Docker Hub transparently, and you can name it. So you can reuse it. If I call that container PyTorch, and I can install a package, for instance, vmtouch, to load datasets in memory. And then if I reuse this container name and I add a mount, it's still the same container, and I will load my dataset in memory. And then for interactive job, if I want a shell inside my container, it's actually, we don't do actually anything on this side. Slurm has a command, has a flag called --pty, and I'm remapped root inside the container, and I can do whatever I want with the combination of Slurm and our plugin. And we have Slurm as batch jobs, so you can have a shell script. You just send this shell script to Slurm with sbatch, and you can run that on 64 nodes, for instance. And here it's something a bit more complicated, but you can have a multi-node TensorFlow job with 16 process per node, and and 5 minutes left. And we reached a conclusion, so we have 5 minutes for question. So we'll have to thank all our colleagues because we've been working on that for a few months at NVIDIA. And that's it. So our runtime and root is open source on GitHub, and our plugin is also open source, and we are open for questions now.
So could you explain a little bit better what didn't you find that you wanted in current HPC container solutions that prompted you to create en route?
So like Singularity, sharded cloud, these kind of things. Well, we reviewed lots of them, and I mean each one of them have their downsides. I mean I could list like all the reasons for each one of them, but we evaluated all of them. The closest one was like sharded cloud, I think, which was the closest in philosophy as like en route. Problem is, like, it was kind of a little too static in our taste, so we wanted something that was way more dynamic, and then like basically we could modify depending on cluster environments. So admins wants to do some stuff in the container runtimes, and sharded cloud was kind of static. So yeah, and they don't use all the tricks that we have listed. So I mean, eventually maybe they will, but right now isn't the case. It was easier for us to write it. And again, there was 500 lines of bash, so it wasn't too complicated.
Perhaps I missed it. Are there any bits that need root privileges in handling the containers?
No. So the runtime itself is fully unprivileged. Now the import, you only have you need one cap to actually mount overlay, but then the actual squash is unprivileged. So by default, we don't allow users to pull images, to convert Docker images. I mean, even though they could do it with like Scopio and Umochi or something, we don't allow that. Because basically it's also discouraging like people from pulling random stuff from the internet. And if the admin wants to allow that, then you can just add one cap on the binary, which is fairly safe because mounting read-only overlay is fairly safe. Ubuntu allows it. Other distributions don't, but no, the rest is fully unprivileged.
Oh, that's gonna be fun. Was it?
So now, since all the focus here is on HPCs on performance, I would like to understand...
Can you put the mic
sorry.
closer? Yeah.
All the focus here is on performance on HPC side. And as a user, I would like to understand if your plan is more to go towards substitute the modules schema, where a single cluster provides you the modules for the software, and you load the module and run your software with the library already pre-configured, or you rather see the cluster IT guys to provide you the container that is with the software specifically compiled for that cluster, or you provide the container to run the software, like TensorFlow, for example. Can I download the application from your side? Should it be provided by my cluster IT guy, or should I compile it myself in your environment? How do you foresee it? Or the module schema is not okay right now, for example? I mean, I see the module schema as the standard.
Right. So the problem with modules and stuff, it's like, I mean, you don't get all the benefits from containers. So it's mostly admin driven, where our needs were more like user centric, where we want a user to bring their own applications. So modules didn't really fit these. We didn't want admins to be really involved in the process of running apps. As for actually compiling stuff specifically for your clusters, we tend to do that with our containers. So,
okay, but if I am, how do you call it? If I am a developer and I develop my software, for example, in my specific case for TensorFlow, okay? I do that, and at the end, if I provide to the end user the container with TensorFlow embedded in it, the flags that I will that I would have used to compile that particular machine would have been the one that fit my own cluster's environment, okay? Not the one of the final user in his own machine.
Right.
Okay, so it will be useless for him at the end, or it won't be the maximum performance that he will get by compiling it on its own machine.
Right, and again, we have a registry where we host all the optimized stuff for our platforms. But again, you can have an admin that just drops squash files that are specifically compiled for your clusters, and then your users can just use the squash file that the admin imported, similarly to modules. Or you can have the user, if he really knows what he's doing, can also push something to a registry and pull that. So we have both use cases covered pretty much. Yeah.
And we're out of time. Thank you.